Normally when we think of computer arithmetic, we think of machine floating point. And for all purposes, we'll consider mostly IEEE double here. This has the advantage that it's fast because of great hardware support. It has a precise mathematical definition, but unfortunately the definition is such that it's not very intuitive to most users. For example, arithmetic is not associative. Some fairly simple computations end up with rather unexpected answers. And in particular, certain kinds of mathematical explorations yield really strange and surprising results. So as the standing example here, we'll use the fact that 1 plus 1 over n to the nth should converge to e as n gets large. In fact, its actual behavior in floating point is much more complicated. So as a result of this, it can be problematic to use machine floating point where either small errors matter or, probably more importantly, where the results are directly exposed to naive users who will be surprised by some of the results and generally complain that those are bugs. We'll look at a couple of applications for which these apply. The first application is Google's Android calculator app, which was actually described in a prior paper, motivating some of the user interface and general functionality considerations. Here we'll focus more on on a principled way to implement the underlying arithmetic instead. This is exposed directly to floating point naive users, clearly, in fact, almost exclusively so. It also has the interesting characteristic that there are actually some calculations that people customarily avoid, but that you would like to be able to do on a calculator to extreme accuracy. So for example, getting back to the one we mentioned at the beginning, 1 plus 1 over n to the nth should get closer to e as n gets larger. What we in fact see on a conventional hardware calculator here is that this works just fine for n equals 10 to the 10th, in fact surprisingly well maybe, but for 10 to the 20th we get a complete nonsense answer. So we would like to be able to plug in an arbitrary value for n, like 10 to the 100th in this particular case, and still get a good approximation for e, or in fact get a better approximation for e. Not only would we like to be able to do that particular problem, we'd also then like to be able to ask sort of how far is this still away from e? How close do we get with n equals 10 to the 100th? So we want to be able to subtract e from it. And on the next slide here, what I've done is I've multiplied the result by 2, because that happens to get us an interesting answer that normally people would have missed with the conventional computation. The second application consists of testing floating point arithmetic. So in this particular case, we happen to maintain an implementation of the Java math library, and we would like to be able to check that if we plug an arbitrary value into those math functions, we actually get something that meets the precision specification that's required by the official spec. We'd like to be able to do that by just evaluating the expression on the slide here and checking that the result is less than the allowed tolerance, the tolerance that's allowed by the spec. This requires that we be able to essentially evaluate this expression exactly in order to check that the result that holds. The standard way, more or less, to approach such a situation is to use something called the recursive reals. These have the advantage that they produce, in some sense, exact results, which can then be used to compute arbitrarily precise approximations from that result, which for all purposes turns out to be almost good enough, but not quite. One way to view the recursive reals is as representing each real number as a function. The function just produces an approximation to any given precision that's requested. To, for example, add two recursive reals, we just produce a function that evaluates the corresponding functions for each of the arguments and then sums them to produce the approximation required for the result. To compare two recursive reals, We simply iteratively evaluate them to higher and higher precision until we get to the point that we can distinguish them and tell which one is greater. Unfortunately, this has the disadvantage that it diverges for equality. This is inherent in the general case. It's easy to show that equality comparison of recursive reals is undecidable, and it also appears to be the case in practice for recursive reals produced by calculator-style operations. The fact that equality is undecidable has a number of unfortunate disadvantages which are listed here. Probably the most important ones are that domain errors such as dividing by zero can't be recognized and reported properly and instead result in timeouts. Another one is that if you're simply adding up your restaurant bill, the calculator won't be able to tell that the answer is in fact finitely representable and therefore should not be followed by lots of zeros, in our case an infinite scrollable sequence of zeros. Our approach accepts that we can't in general decide equality, but it also observes that in many cases, in fact, comparisons are easily decidable. So the way we expose this is we add a function to the API called isComparable, which tells us ahead of time whether comparisons of two real numbers are guaranteed to succeed. Arguably, this reflects user expectations in computing with the real numbers. If I ask you whether e to the pi times the square root of 163 is an integer, you might have a hard time computing that, and you probably wouldn't expect me to do so quickly. On the other hand, if I ask you whether two integers are exactly equal to another integer, you expect that to be a decision that I can make fairly easily and quickly, and that a computer should be able to make. In order to support this, we use a slightly augmented representation of the recursive reals, which is based on a standard recursive reals implementation. Each real number is represented as a bounded rational times a recursive real. Whenever we can, we store not only the recursive real factor in using its usual representation, but we also store a symbolic representation. You'll observe that this is redundant in that if I constrain the bounded rational factor to 1, I can still store every possible recursive real number, and we use that as a fallback representation when we have to. The symbolic representation is quite constrained. The symbolic representation is either one of two constants, 1 or pi, or it's a simple application of one of a finite set of functions to a bounded rational argument. In addition, it turns out it's sometimes convenient to, rather than using one of those symbolic representations, we actually just remember the fact that a number is irrational, and that generalizes things a little bit. We then implement our various arithmetic operations so that they maintain symbolic representations whenever they can, and fall back possibly to the representation as just a recursive real number in those cases in which they don't. The core observation that makes all of this useful is that given our particular choice of symbolic representations here, it's easily possible to normalize a symbolic representation so a represented number is rational only if the recursive real factor is actually 1 and its symbolic representation actually is 1. This has some very nice consequences for comparisons. If we're comparing against a known rational, then we have to be in one of two cases. Either the other number is also a known rational, in which case it has a symbolic representation of 1, and we can just compare the rational representations directly. Or the other number has some other symbolic representation, in which case we know it's irrational, and the iterative comparison procedure for recursive reals will just work because we know they can't possibly be equal. An irrational can't be equal to an irrational number. So this is guaranteed to converge. Even if neither operand is rational, we can still often determine that based on the symbolic representation, that they can't possibly be rational multiples of each other, and hence the two numbers being compared can't possibly be equal, in which case the iterative approach to comparing recursive reals will still work. Again, this relies on the Lindemann-Weierstrass theorem, along with some other observations that are made in the paper. For our first application, Google's Android calculator, our qualitative results have been quite positive. The calculator provides scrollable results so you can get arbitrary precision. It, in our experience, very rarely provides that inappropriately for results that can be finitely represented. The calculator has now been installed on about 500 million devices according to Google Play. The arithmetic implementation is actually quite compact. It's about 6,000 lines of code, including the recursive reals package, so it doesn't add much to the calculator size. We've not received any complaints about erroneous results, excepting concerns about the way we parse calculator expressions, and that's basically something that nobody can agree on. We've not received complaints about domain errors resulting in timeouts. That seems to not happen in general. We've also not received complaints about excessive computation time. It turns out the symbolic representation actually is potentially quite useful to the user as well, and we recently started exposing that in the UI. The performance is entirely adequate for normal calculations. In fact, some things that you would expect to be rather expensive are quite manageable. So for example, if we go back to 1 plus 1 over n to the nth power, we can evaluate that for n equals 10 to the 10,000th in under a couple of seconds or so that there's not really a very noticeable delay. We implemented our second application, checking code for double precision Java functions, and that also has been quite successful. We now have checking code that uses relatively naive comparisons to check the results for division and many of the Java lang math functions, including the trig functions and inverses, exponential and log functions, and the hypotenuse function. It turns out that for all of the ones I've listed so far, is comparable actually always returns true. If we look at the pow function, the binary power function, that's actually not the case. We can still use our package to perform checking, but we have to sacrifice the guarantee of convergence here, or we have to approximate the comparison results. In this case, we've actually approximated the comparison results. In the process of doing so, we found one rather obscure bug in the OpenJDK implementation of the hypotenuse function. But other than that, actually, somewhat to our surprise, everything seems to meet the precision requirements in this spec. In general, checking one function on one argument averages between 300 and 900 microseconds, depending on the particular function we're checking. So the averages vary between 300 and 900 microseconds. And that includes actually calling is comparable in order to check to make sure that the comparisons converge. The challenges we had in doing this is that it's relatively hard to avoid corner cases in the algorithms where the things just take way too long. And since we're actually performing checks on randomly generated floating point bit patterns, those corner cases would initially prevent things from converging in a reasonable amount of time, but we've managed to fix all of those. We actually did one other performance experiment, which is to try to evaluate some large sums using this arithmetic package, as you might encounter in a spreadsheet. Since we don't actually have a spreadsheet implementation, we instead evaluated the harmonic series to some large number of terms between 1,000 and 10,000 and evaluated the result to 1,000 digits. And it turns out that in fact the performance of our package is at least comparable to the underlying recursive real package that we're relying on. And in fact, for this particular example, somewhat surprisingly, it's actually considerably faster in the usual case. And that happens because the net effect of our representation is to evaluate the leaves of expression trees. that evaluate rational numbers using rational arithmetic, which actually turns out to be more efficient. So as a result, we get a nice speed up over the underlying recursive reals package. So in conclusion, we provide exact answers with the expected mathematical properties, and we provide decidable comparisons in cases in which people normally expect that, all sufficiently fast to make this usable for the applications which we targeted. This raises interesting questions about where else this might be usable. It would be interesting to think about this, for example, in an introductory programming class, so students don't have to learn about floating point arithmetic before they can do arithmetic on real numbers. Thank you.